What the heck?
Tagon.
Okay, so today I discovered an interesting little problem on Instagram that I think I would like to solve. This week, since it's Thanksgiving here in America, and I selfishly missed last weekend as well, this is just going to be a series of quick little geometry videos that I'm going to throw up for the next couple days. So I hope you enjoy the little problems, and stay tuned for one of these kinds of problems appearing in a certain calendar later on. Very fun. Alright, so the problem that I found on Instagram today, and I will link to the post in the description. You start with a semicircle. Is that even remotely visible? Barely. Barely. Let's try that again. And then inside that semicircle you're going to put an isosceles triangle, but you're going to do it in a particular way. You're going to put the corner, one of the corners of the isosceles triangle there, and then you're going to put the other two corners such that one of the sides, so you're going to have one of the sides lie along the diameter, and you're going to have the side that's equal to it coming away from the point and intersecting the circumference of the circle. So one of the sides will be along the edge, and then the side of equal length will come away at some angle and intersect there. So I suppose I should really put that like over here. So here is the center of the circle. We'll call this O for origin. And we'll call this triangle A, B, C. And for the sake of simplicity, we're going to say that OA equals OB equals 1. So the radius of this semicircle is 1. And we want AB to be congruent to AC. So AB is equal to AC. And so we know those facts about the drawing. And I guess we could call this point D if we happen to need it at any point. I don't think that we will, but of course this also means that OD is also a unit length, right? Because it's a radius of the circle. And essentially what it's going to come down to is it's going to come down to being able to solve for the lengths of the sides of the triangle. Because we obviously, the semicircle has area pi over 2, because the circle has radius 1, which means the area would be pi, but we only have half of that. So, of course, this is about 1.57, so our number for the area of the isosceles triangle has to be less than that. But we know that, essentially the question is, if OC and OB are the same length, what is the biggest isosceles triangle that we can get inside of here? And in fact, maybe a more interesting question would be a more general question where the radius isn't 1, and you ask what fraction of the semicircle does the isosceles triangle take up? But of course that's just going to be whatever the area of this is divided by pi over 2. And that will be the final answer there. I'm going to get some less dry pens. Let's consider that radius OB, right? That will subtend, the arc from D to B will subtend some angle theta, or I'm sorry, the angle theta subtends the arc from B to D. And by the inscribed angle theorem, which I have proven before, so if you'd like to visit my video proving that, I can link to it now. You can quite easily derive that this angle here, angle A, has to be theta over 2. If you've had the inscribed angle theorem demonstrated to you, that's pretty clear. Since we know that OA and OB are both 1, that means that OAB is an isosceles triangle as well, which means that this angle here is also theta over 2. Right? And what we're going to want to do is we're going to want to find this side length here, because that will be helpful in solving for the height and the base of the triangle. So essentially what we're going to do is we're going to use the fact that I was able to show in my video about when is an ellipse half over, because you'll notice this is a section of a circle, and because we have chord AB cutting through the circle, so we can learn something from the idea of circles overlapping and what was like the length of this line here, essentially. So I guess I'll show you how we get the length of AB. So we know that the arc here from the dotted brown line to OA is theta, pi minus theta, because this angle AOD is a straight angle, so it's pi radians. Since this is already theta, then this angle over here must be pi minus theta. And if we drop a vertical inside this triangle so that it cuts the opposite sides in half, I know it doesn't look like it does, but I'm sort of stating that it does as a fact that this is an isosceles triangle. We dropped a vertical and we have a radius of 1, so a hypotenuse of 1 on this right triangle. So we know that AE is going to be the cosine of theta over 2, which means the full length AB, which is just 2 times AE, is simply 2 times the cosine of theta over 2. And that is the side length of AB, that is the chord. And likewise, that means that the length AC is 2 times AE, which is 2 times the cosine of theta over 2. All that remains to be found is the height and the base of the isosceles triangle, because then we will have a way of writing the area of the isosceles triangle ABC in terms of this angle theta, which can vary from 0 radians to pi radians, all the while drawing whatever isosceles triangle fits that exact scenario, and we're simply trying to find which one is the biggest, so we're going to try and maximize that function. So we know that the side length from A to C as well as A to B is precisely 2 times the cosine of theta over 2, where theta is the angle BOD, and that is subtended by the arc BD. So let's just find the height and the base. So we know we have a triangle, essentially, that is isosceles, and so if we were to drop a vertical from A down to the side length BC, it would be a perpendicular bisector, so it would intersect at a right angle and cut BC in half, which means we would have 2 congruent right triangles put together, which means we could easily solve for the pieces here. So let's do that. So this is ABC, so this is A, B, C. I've turned it so that BC is now the base of the triangle. We know that angle CAB is equal to theta over 2, and that's all we really need to know. And then we just drop a vertical, right? Drop a vertical, that's a right angle. These are the same. This angle is theta over 4, because now we've cut theta over 2 in half, so this is theta over 4. And we know that the side length AB is 2 times the cosine of theta over 2. So this length here is 2 times the cosine of theta over 2 times the sine of theta over 4. But we don't want just half the base, we want the full base, which means BC is equal to 4 times the cosine of theta over 2 times the sine of theta over 4. And this height of the triangle, down from A to the middle point of BC, I guess we can call that F, right? So we'll call that point F, which means F is like somewhere over here, right? The midpoint of BC. So AF is now just the hypotenuse times the cosine of that angle. So we have AF is equal to 2 cosine theta over 2 times the cosine of theta over 4. And now we want the area of the triangle, so we just multiply these two things together and divide by 2. So the 1/2 will cancel with that 2, and we'll get 4. So the area is equal to 4 times cosine of theta over 2 times cosine of theta over 2 again, so cosine squared of theta over 2, times sine of theta over 4 times cosine of theta over 4. And so this is the area of the triangle ABC given this angle theta, as it's inscribed in the semicircle as I've drawn it. We can actually simplify this expression a little bit. We can drastically simplify it, actually. Because what we'll end up with is we can take a factor of 2 from the 4, and then we can do 2 times sine of theta over 4 times cosine of theta over 4, which is just the double angle formula for the sine. And so we'll end up with 2 times cosine squared of theta over 2, and then the factor of 2 from here, this sine of theta over 4 and this cosine of theta over 4, all multiplied together to give us sine of 2 times theta over 4, which is simply theta over 2. But naturally we can do that again with another factor of 2, because we can use 2 times cosine of theta over 2 times sine of theta over 2 to use the double sine angle formula again. And so we'll end up with the one last cosine of theta over 2 times 2 times cosine theta over 2 times sine theta over 2, which is simply the sine of theta, given this angle right here. So I'm going to erase this because we're going to want to know when this is the biggest that it can be. What angle does that happen at? What is the area? And maybe more generally, what is the fraction of the semicircle that that area takes up? So we're going to want to take a derivative of this function here. So this is area as a function of theta. So the area as a function of this angle here. So as a function of this angle here, the area of this triangle as a function of this angle theta, A of theta, is precisely, as we derived, sine of theta times the cosine of theta over 2, right? And we want to know for what theta and what is this area maximized and what is that maximum area. So we just need to take the derivative of this with respect to theta. So A prime of theta is simply cosine theta times cosine of theta over 2. That's the f prime g part. Plus f, which is sine of theta, times g prime, which is going to be negative 1/2 times sine of theta over 2. That's just the derivative of cosine of theta over 2. And this is the rate of change of the derivative as theta changes constantly. And now we want to set this equal to 0 so we can solve for the theta that makes it as big as possible. So we set this equal to 0. And now we're simply going to solve for theta. So I'm gonna bring this negative 1/2 out to the front and then add that whole negative quantity to the other side, and then multiply that 2 over to the other side. So what we end up with, and I hope you can see how I've gotten this, we end up with 2 times the cosine of theta times the cosine of theta over 2 is equal to the sine of theta times the sine of theta over 2. And now all I'm going to do is I'm going to divide both sides by sine and both sides by cosine of theta over 2. So I end up with the pretty nice result that 2 times the cotangent of theta is equal to the tangent of theta over 2. Because I just divided both sides by the sine, so I got cosine over sine of theta, and then I divided both sides by cosine over 2, so I got sine over cosine of pi over 2. So I end up with 2 times the cotangent of theta equals the tangent of theta over 2. Whatever angle satisfies this is also the angle here that maximizes the area of this triangle. And so it's not too hard what we might want to do from here. We're just going to want to take the arctan of both sides and multiply by 2. So we end up with the result that theta is equal to 2 times the inverse tangent of 2 times the cotangent of theta. So let's see if we can figure this thing out. So we're going to want to maybe draw a triangle, I guess. So the best idea that I can think of to solve this problem now from here is to use the tangent double angle formula. Because I can just multiply both sides by tangent of theta to get this result, that 2 is equal to the tangent of theta over 2 times the tangent of theta, because cotangent and tangent are reciprocals. But then I can use the tangent double angle formula for this to get it in terms of tangent of theta over 2. So I get that 2 is equal to the tangent of theta over 2, and now I'm just going to multiply by what I get when I do the double angle formula for this. So imagine this was tangent of 2 times theta over 2. We could then use the double angle formula to write this. We get 2 times the tangent of theta over 2 over 1 minus the tangent squared of theta over 2. And you'll notice that this very quickly becomes a quadratic formula. And so what we end up with is we multiply this thing over to the other side, 2 minus 2 times tangent squared of theta over 2 equals 2 times tangent squared of theta over 2. But of course we can add this 2 tangent squared of theta over 2 to the other side, and we get that 2 is equal to 4. 4 times tangent squared of theta over 2. But of course we can divide both sides by 4. We get that tangent squared of theta over 2 is equal to 1/2, which means that the tangent of theta over 2 is equal to 1 over the square root of 2, which tells me that theta over 2, so that tells me that theta over 2 is equal to the inverse tangent of, this is equal to the square root of 2 over 2, and that is of course equal to pi over 4, and then we simply multiply the 2 over to get that theta is pi over 2, really? Doesn't that feel kind of lame? That almost doesn't feel right. Hang on. Oh, I've made a mistake. That's why. So this is root 2 over 2, but it's the arctan of 1 that is root 2 over 2. Or, I'm sorry, that is pi over 4. This is saying that theta is equal to 2 times the inverse tangent of the square root of 2 over 2. But what is the inverse tangent of the square root of 2 over 2? That's very strange. So let's see if we can work that out. The angle that is in the inverse tangent of... Oh, it doesn't really matter, I guess. So we know that... So we've got the area function, we've got the derivative of the area function, which is cosine theta times cosine theta over 2 minus 1/2 sine theta times sine theta over 2. And we've just discovered that the derivative is 0 at theta equals 2 times the inverse tangent of the square root of 2 divided by 2. And so if we want to know the maximum area that we get from that, we don't really need to calculate what this number is. We sort of just need to plug this theta into a of theta, right, into the function that describes the area. So if we plug this into that, let's see what we get. So we get, so if this is, since we're using Greek letters, let's call this mu for maximum, right, just to be super Greeky, yeah. So theta is now mu, which is this quantity here. So we get the sine of 2 times the inverse tangent of the square root of 2 over 2 times the cosine, and this 2 and that 1/2 are going to cancel, so we're going to get the cosine of the inverse tangent of the square root of 2 over 2. And now we just need to calculate these two things, right? The sine has a double angle formula, so this can be rewritten as 2 times the sine of, turns out we probably should have kept it the other way it was written. So we get 2 times the sine of the inverse tangent of the square root of 2 over 2 times, and now this, we're going to get the cosine of that thing from here, and we have another one there, so we're going to get cosine squared of the inverse tangent of the square root of 2 over 2. So essentially what we need to do is we need to say that we have an angle, theta, that we don't know. Since this angle is inverse tan of root 2 over 2 instead of 2 times the inverse tan of root 2 over 2, what we're about to do is really mu over 2. Since we call this is mu over 2, and so we know that the tangent of this angle is the square root of 2 divided by 2, also known as 1 divided by the square root of 2, right? The tangent of that angle is 1 over the square root of 2. 1 squared plus this squared is 1 plus 2, which is 3, which means this side is the square root of 3. Which means now we can solve for the sine of this angle and the cosine of that angle and simply multiply it out. And so we get that the maximum area is 2 times the sine of this angle, which is 1 over the square root of 3, times the cosine of this angle, which is root 2 over root 3 squared. So we get the square root of 2 divided by the square root of 3 squared. And so we end up with 2 times root 2 squared, which is 2 times 2, and that's 4, divided by root 3 squared is 3, times the square root of 3, which is 3 times the square root of 3. Of course, this can be rewritten as, and rationalized as 4 times the square root of 3 over 9. And that is the maximum area of an isosceles triangle in a semicircle where one of its corners is on the circumference and one of the sides lies along the diameter. 4 times the square root of 3 over 9. Of course, if you wanted to know the fraction of the circle that takes up, the semicircle I mean, and since the semicircle is pi over 2, we simply have to divide this amount by pi over 2, which just amounts to multiplying the numerator by 2 and multiplying the denominator by pi. So the fraction of the semicircle that this largest isosceles triangle takes up is precisely 8 times the square root of 3 divided by 9 pi. A very interesting number, and that's the answer to the question. So this is the area of the triangle, this is the fraction of the semicircle that it takes up. Cool, alright, well I hope that was very enjoyable. Check out the Instagram page where I got this from, it's a very neat little math puzzles page. I don't quite remember the name, so I'll just post it, a link here and in the description. Thank you very much for watching. Have a wonderful Thanksgiving. Bye-bye.